Our lesson here is integrals involving inverse trig functions, because those derivatives are kind of different. So the derivative of sine inverse, remember, is 1 over the square root of 1 minus x squared. So the integral of 1 over the square root of 1 minus x squared is sine inverse. So here, this would be sine inverse from 1/2 to 0. So we have sine inverse of 1/2 minus sine inverse of 0. So we're looking for on the unit circle between negative pi over 2 and pi over 2, where sine is 1/2. So that's going to be at pi over 6. And then sine is going to be 0. So our answer here is pi over 6. The derivative of tangent inverse is 1 over 1 plus x squared, or x squared plus 1. It can go in either order. So the integral of 1 over 1 plus x squared is tangent inverse, and we've seen this one a couple of times already. So for this one, we have the tangent inverse evaluated from 1 root 3. So we have tangent inverse of root 3 minus tangent inverse of 1. So we're looking for on the unit circle where tangent is root 3. That's going to be up at pi over 3. Tangent inverse of 1 is pi over 4. So this would be 4 pi over 12 minus 3 pi over 12 is pi over 12. The derivative of secant was 1 over absolute value of x times the square root of x squared minus 1. So the integral of this, even though there's not the absolute value, we accept that to be secant inverse of x. This one then is going to be secant inverse of x evaluated at 2 over root 3 from root 2. So that's going to be the secant inverse of 2 over root 3 minus secant inverse of root 2, which is equivalent to the cosine inverse of root 3 over 2 minus the cosine inverse of root 2 over 2. That's going to be pi over 6 on our unit circle minus pi over 4. So we'd have 2 pi over 12 minus 3 pi over 12, which would be negative 1 pi over 12. We're going to focus on just sine inverse and tangent inverse. Secant inverse rarely comes up in, really never comes up in an AP problem, but sine inverse and tangent inverse do. All right, so we're going to focus on sine inverse. So we have the integral of a squared, not just 1, and we're saying this is equal to this. So we're going to prove this just by taking the derivative of sine inverse of x over a. Well, that's going to be 1 over 1 minus x over a squared times the derivative of that, which is going to be 1 over a. Okay, so we're trying to transform this to look like this. So I'm going to rewrite this as 1 over the square root of a squared, because then I can multiply that in. So 1 times the a squared is just a squared, and then x squared over a squared times a squared is x squared. So if we have the integral of 1 over a squared minus x squared, then it's the sine inverse of x over a. So you'd want to make that into a note card or add it to your integral list. All right, so this first one is just applying the rule. I've got a squared minus x squared, my a being 5. So this is just going to be the sine inverse of x over 5. Here, I have I don't have an x squared. So I'm going to let u equal 5x, which means du is 5 dx. So I'm going to put a 5 in here, undo it with a 1/5. So this is going to be 1/5 times the integral of du over the square root of 1 minus u squared, because 5x squared is 25x squared. So this is going to be 1/5 times the sine inverse of u, which is going to be 1/5 sine inverse of 5x plus c. I'm going to do the same thing here. Let u equal 5x, du will equal 5 dx. So we have the square root of 9 minus u squared. So that fits our pattern, just like this one. So this will be 1/5 times the sine inverse of u over 3, which is going to be 1/5 times the sine inverse of 5x over 3. All right, now we're going to prove that the integral of x squared 1 over x squared plus a squared is 1 over a tangent inverse of x over a. We're going to do this again by taking the derivative of this. Well, that's going to be 1 over a times 1 over 1 plus, instead of x squared, x over a squared, times the derivative of that, which is 1 over a. So we have 1 over a times 1 over a will be 1 over a squared, times 1 over 1 plus x squared over a squared. So then we can just multiply this through. Get 1 over a squared times 1 is a squared times x squared over a squared is x squared. So the integral of this is 1 over a times the tangent inverse of x over a. That'd be another note card. Right? So this is equal to x squared plus a squared, where a would be 4. So this will be 1/4 times the tangent inverse of x over 4. Okay, here I'm going to do a u substitution. U equals cosine of x, or theta. So du is going to equal negative sine theta d theta. So this will equal a negative integral du over 1 plus u squared. So this is going to be negative tangent inverse of u, which is going to be negative tangent inverse of cosine theta. Okay, here we're going to let u equal e to the x. So du is going to equal e to the x dx. So this is now the integral of du over 4 plus u squared. E to the 2x would be the same as e to the x squared. So this is going to be 1/2 tangent inverse of u over 2. So we have 1/2 tangent inverse of e to the x over 2 plus c. In our next unit, we're going to be doing volumes. So this integral, and you can read all of this about where this comes from. But this is the integral from 1 to b of 2 pi x times 1 plus x to the 4th. So I'm going to do a u substitution with x squared, because this is going to be x squared squared. So this is going to go from b squared and 1. du is going to equal 2x dx, which I have there. So this is now going to be the integral from 1 to b squared. The 2x dx, 2x dx gets replaced with du. So we are going to have the pi. I'm going to go ahead and bring that out here. Okay, and then our u, or x squared squared gets replaced with u squared. So this is going to be pi times the tangent inverse of u, evaluated from b squared to 1. So tangent inverse of b squared minus tangent inverse of 1, which is going to be pi. This we can't do anything with at this point. Tangent inverse of 1 is pi over 4, though. Okay, we're going to do these ones by completing this square. So here I'm going to have the integral. I'm going to have x squared minus 2x plus something plus 5 minus that something. So you're trying to find the value that would make this a perfect square, or you take this, divide it by 2, and square it, which in this case is going to be 1. So this is a perfect square. This is going to be x minus 1 squared plus 4. So this is tangent inverse. It's just instead of x squared, we have x minus 1, but that's okay. And if you want to do u substitution, you can. But since this is 4, we're going to have 1/2 tangent inverse x minus 1 over 2 plus c. All right, this one looks pretty simple, but it's actually going to be a little bit tricky. So I'm going to complete the square again, but it's the same denominator that we just did. So this is now going to be dx over, this is the same thing, so x, not d, 2x plus 1 over x minus 1 squared plus 4. So I'm going to let u equal x minus 1. But I still have this numerator. So I'm going to solve this for x, and I'm going to make some replacements here. So instead of 2x plus 1, I'm going to have 2u plus 1 plus 1 over u squared plus 4. So this is going to be 2u plus 2 plus 1, so that'll be plus 3 over u squared plus 4. Okay, so this one I'm now going to split up into two different integrals. I'm going to put the 2u with u squared plus 4, and I'm going to put the 3 with u squared plus 4. Okay, because I can split up that numerator. This one, I'm going to do a u substitution, but since I've already used u, I'm going to make w equal u squared plus 4. So dw is 2u du. So this integral is now the integral of dw over w. This one is going to be 3 times 1/2 tangent inverse of x over, or u over 2. All right, keep plugging away. So this is going to be the natural log of the absolute value of w plus 3/2 tangent inverse of u over here was x minus 1. W is u squared plus 4. So u is x minus 1. And copy all the rest down. So that was a sort of complicated one, but it just involves a lot of the different techniques all in one problem. So that is integrating with inverse trig functions.